Let's dive into the paper. If you were here a month ago for R1, this presentation will be quite different because R1 had a lot of math and a lot of novel ideas. And S1 is quite different. S1 has effectively two very simple ideas behind it, but those simple ideas result in very good results. So there's going to be way less of hardcore math and more of interesting ad hoc engineering. So two ideas behind the paper are, and they largely, I guess they both contribute towards the end goal, but they're largely independent. One is a particular data set, which only consists of 1,000 examples, which is extremely few, that when you train on it, makes the model significantly smarter. And these 1,000 examples are distilled from a larger data set of 59,000 examples, which is more of the size of what people usually use for fine-tuning. And those 1,000 examples give you almost the whole benefit of the entire data set, right? So if you fine-tune on that 1,000 and on all 59,000, you get the model of very similar capabilities. And the second idea is called budget forcing, and it's a very nice, very simple trick which you apply at test time, at inference time, which makes model smarter, but also it makes model work. Like depending on the question at hand, you can force her to work cheaper or spend more compute to get to the result faster, or to get to a better result. Okay, let's talk about the data set. So the data set, the goal that they had was they started with the Qwen32b, and they wanted to make Qwen32b smart. They wanted it to do reasoning, sort of like what R1 does, provide the result, and they wanted it to be as smart as possible. And their first idea was that the data set on which they're going to train needs to be sufficiently diverse. If the data set is homogeneous, then the model will over-optimize for a particular area of expertise of that homogeneous data set. And so they outline all the sources that went into the data set, and you will see that some of them, most of them are mathematics, but even within the mathematics, they're quite diverse. They spend combinatorics, algebra, geometry, etc. And some of them have, like Olympiad Bench is a data set that goes into other STEM disciplines, not mathematics specifically. Then there's English, law, brain teasers. So it's a very sufficiently, you will notice that the majority of examples is still math, right? The first two combined is 42,000 examples out of 59. So it's still predominantly math, but it has sufficiently many examples from other areas. And every entity, so the data that they pull together is a problem, and most of the problems have solutions, not all of them. By solution, I mean the final answer. But I don't think any of those data sets have the actual reasoning trace annotated by a human, right? But in their data set, they do want to have a reasoning trace. They want to have a problem statement reasoning, something like what R1 or O1 would do, and the solution, which is, again, answer. The way they do that in the original, so the paper was written, I guess, and then when they were ready to publish it, R1 came out. But because they did most of the work already on the original, they didn't change. And so majority of the paper is written based on Gemini flash thinking, which is a Google's model that allows you to get those reasoning traces. But then at the end, they mentioned, hey guys, when the paper was ready to publish, R1 came out. So we tried some of the experiments using R1 instead of Gemini flash thinking. And everything that uses R1 was significantly better. We will get to the results. Right, but what they do here is that they get the problem statement, give it to Gemini flash thinking. She generates a reasoning trace, an answer. Okay, and then they want, when they distill those 59,000, right? So they put this goal in front of themselves, right? They have these 59,000 examples. They want to get 1,000, and their goal is to get that 1,000 to be as good as possible in terms of the final model performance. And they identify three qualities that those 1,000 examples should have. One of them is quality, and when it comes to quality, it consists of two steps. The first step is they just filter out a lot of garbage, right? So while they were doing Gemini thinking, there were some API errors, some of the output was not parsable and whatnot. It only gets rid of a small number of examples. Then they do difficulty, and then after difficulty, there will be a second step of quality. When it comes to difficulty, what they do is they get the problem, send the problem, and the number of models that they use in the pipeline will be growing very fast, right? They send it to Qwen 7b and Qwen 32b, and if neither of them solves it, they consider that example as a good example, right? And the reason they use two models and not one model is that with one model you can have, it could be a very easy problem, but the model just, I don't know, like you know, models mess up, right? So with two models, they reduce the chance of such simple problems of slipping through. And the way they derive whether the model solved the problem is they get the solution of the model and they get the answer that they have, right? And the model also produces the answer. I guess in many cases they could just compare it, but they don't do that. Instead, they get the solution of the model and the answer, and they feed it to Claude 3.5, and they say, hey, Claude, look at this solution. This is the answer we know that is correct. This is the solution and an answer. And you know, if the answer is, actually, maybe I have it here. No, I don't. And if the answer, you know, is specific, just compare them. And if it's not specific, look through the solution, tell me if it's good, right? So Claude is the final arbitrator of whether the solution is correct or not. And so they filter out of 51,000 examples that were remaining after removing garbage, they filter it down to 25,000, right? So, which in itself is interesting. I guess it's an interesting quality of the data set, of the initial data set, right? That Qwen 32b, which is a relatively capable model, was not able to solve half of the problems. Okay. And so once that is done, the third part is diversity. But first, speaking of quality, so they want to get 1,000 examples. And the first thing they do is they say, if the Gemini solution was correct, as judged by Claude, and it's one of the very high quality data sets, IME or GPQA, then they just put the example into the data set, right? And if it's also if it's correct, and it's math, any math, doesn't have to be from those two high quality data sets, but the thinking length is very long, right? So Gemini, and Gemini is not instructed in any way for how long to think. She decides, right? So if she chose to think for a very long time, more than 6,000 tokens, they're like, hey, that must be a good example as well, because presumably longer thinking correlates with the harder problems, right? And that results in having 384 problems out of 1,000 they want to have, right? So they need to get the remaining 600, 16. And that's where the third quality comes in, which is called diversity. They want the 1,000 examples to be as heterogeneous as possible. The way they do that is, again, they use Claude to assign labels or like tags to problems, you know, combinatorics, biology, geometry, algebra. So they have those domains, and there's a picture in the paper, I don't have it on the slides, which shows like a tag cloud of how many problems they have of each in each domain, and it's pretty much evenly distributed, right? And so what they do is they say, you know, until we have 1,000 examples, we sample randomly one of those domains, and from that domain, we get one of the examples, and the way they get an example is they build the power law distribution over the lengths of the thinking, and they favor examples which have longer thinking. And as a matter of fact, if you look at the exact formula, they favor them drastically. If I'm reading it correctly, right? If you look at lines 2021, 2022, effectively the longest sequence will have 50% chance of being chosen. The second longest will have 25%, etc. Right? Because the weights is 2 to the power of the rank, right? So the longest one will have weight of 0.5, the second longest will have weight of 0.25, etc. Right? So the longest ones will get chosen disproportionately frequently. Cool, and they do it until they get to 1,000 examples. So the goal here is to get, you know, you see when they choose the domain, it is not weighted, right? It is not weighted by the number of examples in the domain, right? So they want the final data set, the remaining 616 examples, to be, representing every domain equally, and among those, get the most complex ones. Okay. Oh yeah, so grading is how they were. Okay, I do have the prompt. This is the prompt they were giving to Claude. It's in the paper to tell if the answer is correct, right? And it was used in two places. It was used here when they were trying, to get the first 300 examples, which are of extremely high quality. And it was used to decide to begin with if they want an example, right? So if Quen would already give you an example that give you a solution that Claude deems correct, they don't even want to have that example in the data set. Right, and something interesting that I guess is worth highlighting here is that while the first 300 examples all had a correct solution, the lower part of the algorithm does not check for correctness, right? So they will sample incorrect solutions, and moreover, as it says here, the actual model, the actual data set that was used for the majority of the paper only had 53% of the problems solved correctly in the data set, right? 47% were incorrect, which I think on itself is very interesting, right? Because you like one of the goals is to create 1,000 high quality examples, and yet like they go at length, to devise those algorithms, and yet they end up having only 53% of correct solutions, right? And presumably it is not something they do in ablation testing. They do a lot of ablation, but they do not test what would happen if they only got the correct solutions, which would be very interesting to see what happens, right? And so S1K 1.1 is the one that they mention in Appendix A. That is the one that uses DeepSeek R1 instead of Gemini Flash Thinking. That one has 63% correct solutions. Cool. So that's the data set, right? So once the data set is ready, they fine-tune Quen 32B on that data set, and then they test it with the second idea in the paper called budget forcing. The idea of the budget forcing is that they want to, for a particular problem, they have a problem, they want to solve it, they want to have a particular budget in terms of tokens, and they have both a lower bound and an upper bound in that budget, right? And they want the model to be thinking within that band, right? And like in many cases, you don't want it to think shorter because you want, you're like, hey, I have more resources, think longer, but do come up with a higher quality answer, right? And they don't want it to think much longer because you have limited resources that you're willing to spend. And so when they want to limit how the upper bound of the model thinking, that's relatively straightforward. You just, if you reach the upper bound, you just insert end thinking token and say, hey, final answer is, and the model presumably will stop thinking and produce the answer, and that's exactly what it does. But continuing to think is a more interesting idea, right? So the simple idea would be to just say, if it tries to create end of thinking token, you just sample any other token, right? Because, like at the end of the day, you choose which token to sample, right? You just say, until I reach the lower bound, I will not even consider, I will mask out end of thinking token, right? So it will have to continue thinking indefinitely. And so they do test against it. That's one of the ablation tests. And they found that it is not the best way to do that. The best way to do that is whenever you see end of thinking, to sample weight instead, right? So it thinks about, it thinks reasons, then it's ready to give you the answer. It says end of thinking, and you suppress end of thinking, and instead sample weight, and maybe triple dots, I don't remember, right? So weight, and then the model has to continue from that state after weight, right? And so it will, it will challenge her assumptions and presumably think further. And so this is the results on a data set called AIME 24. It's 30 problems. I think that was a qualifying round for US Olympiads in mathematics, right? So it's a pretty complex 30 problems. And you will see that the x-axis is how many tokens it can think for, right? So if it's 1,000, so generally when we will see it in future tables. Generally, if you do nothing, on average, model thinks for between like 5 and 6,000 tokens. This is a reasonable thinking trace, right? So if you wanted to think for 1,000 tokens, that means you will almost always have to cut it short, right? So like it will mid-sentence, you will insert end of thinking and send it to get the answer. And similarly, you will notice on 2,000 and 4,000, it's also effectively more often than not you will be forcing it to stop. While for points to the right, this is where it would actually try to stop earlier, and they introduce this wait interference, and not entirely surprisingly here, right? The longer it thinks, the better it solves, right? So at 1,024 thinking tokens, it barely solves. I guess 0 is not 0 here, right? That would be like what, 16%, right? But it reaches almost 60% as it goes up. And I think very interesting comparison they make here is very interesting comparison they make here is that there is another way to spend more tokens during test time, right? So like let's say that an average thinking trajectory is 5,000 tokens, but you at test time have sufficient resources to spend 20,000 tokens. What you can do is you can unroll 4 thinking trajectories, and in each of them come up with an answer, and then it's called majority voting, and then you choose the answer that is the most frequent answer among those, right? Because there are many ways to mess it up, but there's only one way to solve it correctly, right? So if you solve 1,000 times, and 100 of those, the answer was 5, and in the remaining 900, it was all over the place, then the answer is probably 5, right? It's called majority voting. And you will see here that with the same budget, sequential scaling, so, making a single longer thinking trajectory scales much better than doing majority voting. And motivation behind it is that with a single trajectory, every consecutive token sees all the mistakes the model has made. But with parallel scaling, they have to redo all the mistakes again. Okay.
It's not a very fair comparison because the use of temperature equal to 1 for the parallel scaling, by using temperature equal to 0 for the S1 model. And I think that in general, in more scientific setup, a lower temperature, interestingly gives you a more accurate answer. So it's just an example.
All right. So this
experiment using the same temperature.
Yeah.
To make sure everything is fair.
Yeah. So the note was that the parallel scaling here uses temperature 1 and the sequential uses temperature 0. I guess you cannot quite use temperature 0 for parallel, right? Because you will get the same trajectory. But I guess you can use lower temperature. That's or I guess for fairness, what you can do is you can use temperature 1 for sequential. That would make for. I see. Okay. Okay. The results, and there are 2 tables for the results in the paper. One is in the actual paper, which I don't have here on the slides, and then another one. This is from Appendix A. This one has S1.1, the one that was trained using DeepSeek, and this particular table is missing one of the rows that the table in the paper has. Specifically, this table doesn't have Qwen32b, which is a very interesting benchmark because Qwen32b is the base model for SK, right? And so, okay, a couple observations here. One is that the resulting model is not even close to 03, which is presumably something we would expect. And yeah, in the original paper, they also have 01, and 01 numbers are also noticeably better than S1. Then, if you compare it to R1, R1 is also better. So this is a misspelling. This is a typo. That is actually 97.3. Right, but if you compare it to distilled, but R1 is the one that is the result of the actual reinforcement learning, right? It's not a fine-tuned model. It's significantly more compute, right? So it's interesting to compare to the distilled models, right? Because a distilled model is distilled on. So this is a very interesting comparison, right? These 3 rows is three models. And I guess the most interesting one would be Quen32b because it's the same base model, which is fine-tuned on 800,000 examples, right? 800 times more from R1, right? And you will notice that S1 is outperforming it on all three, not on IME, but it's outperforming it on Math 500 and GPQA, right? So while only being trained on 1,000 examples, right? So it's an interesting comparison. And the base numbers for Quen 2.5b is on IME it would be 26%, right? So like the improvement relative to the base model in both cases, in both distilling from R1 and training on S1 is significant, right? Effectively, it solves twice as many problems as the base model. Cool. And here you will notice they also show the result. So first of all, you will notice that the model trained on DeepSeek trajectories is noticeably better, S1.1, than the one trained on Gemini. Also not surprising. And it shows the result of introducing those weight, forcing it to think longer. You see it gets like an extra % on Math 500. Extra 2% on the GPQA. Cool. $14B. Oh, you mean for Amy, right?
Yeah.
Yeah.
I think the big ball.
So S1.1 is 32B, right? Yeah. Well, a more interesting question here is why the result of the distilled 32B is lower than distilled 14B, right? So I guess there's a couple of things here. One is that generally the benchmark is not very accurate, right? There is some randomness involved.
So I'm gonna. Well, R1 was also trained on 800,000 Richmond samples.
Yeah. So big difference between this row and this row is that R1 is in fact distilled model was trained on 800 times more examples, fine-tuned, right? It's 800K. No, the distilled one. It's a distill, right? Right. So it has seen way more examples, right? It still doesn't explain why between the two of them, 32B performs worse. But yeah, it's could be some intricacy of a bigger model, right? Like for example, I don't think if it applies here, right? But when you start training, when you pre-train a model, for the first many iterations, the smaller model will perform much better than the larger one, right? It's much later into the training that the large model catches up with the small one, and I don't know if the same applies to fine-tuning, but I wouldn't be surprised if that's something that potentially has an effect here. Okay, so they did some ablations, not as many as one would want. You might always, I don't know, I always want more ablations because there is, if the paper has 10 ideas, in the perfect world you will have 2 to the power of 10 ablations. Not quite what we get, but we get quite a few. So first one is they say, hey, is our sophisticated algorithm of choosing 1,000 examples, is it even necessary? Could we just choose, 1,000 examples using only subset of those ideas, right? And so they test 4 different ideas here. First idea is they just sample randomly, and you will notice that randomly is not doing particularly well. So on IME it solves 36%, which is a 10% improvement over the base model. On Math, so on Math the base model has 80%, right? So they get 84%, so this is 6% improvement. And this on GPQA, the base model has 48%, so that's a 3% improvement, right? So random doesn't give you as much. It still improves the model, but doesn't give you, it's nowhere close to what S1K gets, right? Diverse says we will choose examples from different domains, the second part of the algorithm, but we will do nothing in terms of ensuring the quality. All right, in particular, after choosing the domain, presumably they just choose each example uniformly, as opposed to that weighting where they choose the one with the longest thinking trajectory. Works better on these two data sets, significantly worse on IME. On IME, actually, it does exactly as poorly as the base model, which is fascinating, I guess. Longest. For the longest, they just got 1,000 longest trajectories. No, not looking at all at the domains or quality. Again, it's interesting, right? Because on each data set, it performs differently, right? On GPQA, it does very well, but on math and IME, it's doing much worse than S1K. And the last one is just train on all 59,000 examples, right? Do not remove the ones that were solved by Quen. Do not remove low quality ones. Do not do any. Keep all of them. And I guess the last two are of particular interest, right? Because training on all 59K is actually better than training on 1,000, right? But obviously it's 60 times slower. So it's interesting to see how much, and there's this confidence interval, right? So it's not just 53. The numbers in the square bracket say, hey, within some probability, I don't remember, like 90-something%, it's between -13 and 20% relative to S1K, right? So yeah, effectively, those 1,000 examples, are getting you all the way there to what you would get with 59,000, which is pretty cool. Okay, then in terms of cutting it short or introducing this weight token, they compare against 3 different approaches. In one approach, they just tell the model, think for that many tokens. That just doesn't work. Right, the prompt is on the left, right? It says, hey, what is the answer to this? Think for 2048 tokens, right? And if you think at how many tokens it actually thinks, there's no correlation. The upper part of the table, right? There's no correlation between how many tokens it's instructed to think for and how many it actually does, right? It's no matter what it thinks for 7,000-8,000 tokens, so it completely ignores. It has no inherent ability to understand how many tokens it has emitted so far, which I guess makes a lot of sense, right? Because nothing in its data set was ever presumably mentioning this concept. And you will notice that despite thinking for different number of tokens, it is actually increasing in terms of quality, which is very fascinating. Right, you will see that, even though it was thinking in both cases for almost 8,000 tokens, the quality here is only 26%, which is exactly the quality of the base model, right? And it increases with the number of tokens requested. And on the lower part of the table is they still.
Yeah, like so the measure it does supervise might be most likely equal. So it's actually this time scaling. There's no example of next stage.
Interesting question. So the question is, would it qualify as a test time scaling if it's just a supervised fine tuning? I think when they say test time scaling, they specifically refer to this, saying weight. The data set is just a cherry on the cake in this case in the paper. Yeah. Yeah, but this is not test time, as you properly mentioned, as you properly said. Any sort of supervised fine tuning is train time scaling. When they say test time scaling, they specifically refer to the fact that they can scale the amount of resources you spend at test time by saying wait. The weights are fixed, yes, but the amount of thinking it does scales by saying wait instead of end of thinking. So that's what the title of the paper refers to, not the what? Oh, the chart. There is. I don't know if I have it here. No, I don't have the main chart here. But yeah, it's like the very first chart in the paper shows you that as maybe it was at the beginning. Oh yeah, this one. Yeah. So this is one of them. Yeah. Yeah, so this is entirely test time, right? So how many thinking tokens? That's entirely test time. The model is fixed at this point, right? And the more thinking tokens you spend, the higher is the quality.
Like, do they give an eye? You know, like at what, like, so at what point then, like, the end of the script involved continue and they supervise one thing, did it, or did
No, this is only during testing. When I'm pretty sure when they were doing Gemini, from Gemini they get the whole trajectory, right? They never truncate it and never do weight and whatnot. As a matter of fact, Gemini API doesn't even give you this opportunity. You cannot say, oh, you know what? Do not sample end of thinking here. With R1, they could have done it.
I guess like my finding is that not it he wouldn't have with model. We stop it by not trying. If innovation is that you get token at some point, so thinking it says like that like so
Yeah.
like doesn't actually matter that it's but not like you do get the same self like R1 like you can't like R1 slow model is exactly.
Absolutely. I think the entire point of this paper is that the whole paper was written before R1, right? So I think the motivation why they even went ahead to build this data set, why that even is part of the paper, is that when they were writing the paper, there was no open source thinking model, right? So in order for you to have a model to do this experiment with test time scaling, you had to create one to begin with. And the only thinking model available, I guess, was Gemini that allows you to use it for training. You know, like O1 existed, but OpenAI explicitly prohibits using their outputs for fine-tuning, right? So yeah, so I guess the first half of the paper is there precisely because R1 did not exist. With R1, but it is a very interesting finding that you can use that 1,000 examples. It's still value. Could have been presumably a paper in itself. Yeah, but this S1, the simple scale test time scaling refers, I think, specifically to truncating or introducing weight tokens. Okay, coming back to this ablation, on the lower part of the table, they also instructed to think for a number of tokens, but then they truncate at that number of tokens, right? And I'm pretty sure 3.3 is another typo. I don't think it gets that bad. It's probably 33.3. But yeah, it's yeah. Okay, the second one is interesting because they say think for that many steps, right? And they empirically, I guess, they run some experiments and notice that if you ask her to think for some number of steps, a step on average is 100 tokens, right? And so they came up with the idea of trying to think it. So if you ask it to think for 64 steps, you're looking for like a ballpark of 6,400 tokens, which could be exactly what you want, right? And so they tell the model to think for some number of steps, and then I think the part that says that many number of steps left is also engineered into the model, right? So this is interesting, right? Because this time around, the model obviously does have a concept of the number of steps, right? Because the number of steps is explicitly written that is left, right? So you would expect that it cannot think for more steps than it is instructed, but you will see in practice it does, right? So if it says think for 16 steps, right? And then it says 16 steps left, 15 steps left, 0 steps left, it goes to -1 steps left, and it will continue for on average 123 steps. So that's fascinating that the model after reaching 0 steps left does not forcefully stop thinking, right? And that reproduces for all number of steps all the way to 256, which is also interesting, right? If it says think for 256 tokens, I would also expect the model to always go all the way down, but it does not, right? It stops at some number of thinking tokens. And the results are comparable, right? It's again 33% give or take on every execution.
Yeah.
And again, the same lower half, they truncated at 0 steps forcefully. The results are comparable. An interesting thing here is you will notice that if the model is instructed to think for more steps, the steps get shorter, right? So if you say, hey, do 16 steps, the steps on average are 60 tokens long, right? Well, I guess 60 is an outlier, right? But you see 70, 69, 66, 56, it's gradually decreasing with the number of steps. So, the model is tricking itself into thinking for approximately the same number of tokens. Yeah, and the last ablation they did is they just told her, think for a little bit or think for a lot. And that worked relatively well in the sense that you will notice that when it's instructed, so the first prompt is think for a little bit. The second one says think for a lot. You will see that the number of tokens is in fact much lower in the, not much, but it is noticeably lower in the first case than in the second. And thinking for longer does increase the quality on the first two data sets. Although I think something interesting is the third row here, which I might not understand it correctly. The paper doesn't say anything about it. It only exists in the table, right? But the way I understand the last row is that they run 3 experiments. And the first, they have this after the problem statements. And the second, they have this. And in the third, they just have nothing. And you will notice that having nothing does much better than saying either think for a little bit or think for a lot, which I think is a very interesting observation, but paper completely, completely ignores it. They never mention the fact that not instructing it to think for a particular duration is better. Okay. The last one they do is the rejection sampling. Effectively, this is only any application in the ablation test. You would never do rejection sampling like that in practice, I guess. But what they do is that they would sample a thinking trajectory, and if it does not have the required number of tokens, they will completely discard the sample and sample it again, right? And so they will sample until they get the desired number of tokens, right? Does that make sense? And so interestingly, if you sample until you get, the more tokens you wait for, the worse is the quality, right? So if you sample until you get 2,000 tokens, the quality is pretty good. It's like 40% on IME, which is a decently good result. But if you sample until you get more than 5,000, the quality is suddenly 22%. The way they actually have a whole example in one of the appendixes, Appendix E2. They have an example where they look at one of the problems where this phenomenon occurs, and they observe that the short thinking trajectory is usually the result of the model immediately jumping to the correct idea, and it develops it and it gives you the answer. The answer has high percentage of being correct, while a longer trajectory means that the model initially came up with the wrong idea and then it had to backtrack many times. And so there's a much higher likelihood in this case to never arrive at the correct answer, right? And so that presumably explains this weird, downward-facing graph with a bigger budget of tokens. Okay, the very last ablation, which I think is interesting, right? So, because when they reach the thinking limit, right, they just forcefully sample end of thinking, right, and proceed to the answer. So the natural reverse of that, right, if you want to think longer, you just sample anything which is not end of thinking token, right? So you just mask it out until you get to the desired budget of tokens, right? And so that's a very interesting baseline to compare against, and they do here, right? So the 2x without string is effectively sampling, just masking out end of thinking until you get to the number of tokens you want, and then they introduce different. No extrapolation means they just end of thinking means end of thinking. Just sample it and stop. And then they have different versions of what they can sample, right? And you will see that on that not introducing weight on all the data sets results in a strictly worse performance, right? So if you just force the model to think longer, it is more likely to digress than to improve, right? While sampling weight increases on 2 out of the 3 data sets. And Math 500 is the only one on which it does not improve, but it's already 93%. right? Meaning that, it only has very hard problems left unsolved. Right, so it's interesting, right? Because like I could imagine if someone came up with an idea of forcefully thinking, like if you try this first experiment and you get worse results, it's interesting that people actually went ahead and even tried something else, let alone actually got a very positive result. Okay, cool. This is the last slide I have. That's the paper. Exciting results. Okay, cool. Let's continue conversation back at the pizza stand.